has said, my name is Athleen Clark, and I'm the NOAA Superintendent for Papahānaumokuākea. And Papahānaumokuākea, for those who don't know, is co-managed by 4 major agencies, including NOAA, the Fish and Wildlife Service, the State of Hawaii, and the Office of Hawaiian Affairs. We would like to say mahalo to Hanauma Bay for hosting this month's series on Papahānaumokuākea. And each one of the talks this month is giving you a slightly different flavor of what we do as part of Papahānaumokuākea, and actually how it relates back to the entire Hawaiian archipelago. Just one commercial plea. In early June, we will be commemorating the 75th anniversary of the Battle of Midway. If you are interested in finding out about some of the many activities that will be done surrounding that commemoration, you can log on to midway75.org and you can get a lot of information about what's happening with that, or you can go to the Papahānaumokuākea website and get information there. So if you're interested in additional information about Papahānaumokuākea, there are several places to go. I'd like to now introduce Dr. Carl Meyer. And Carl and I have worked together off and on for many, many years. As a matter of fact, I was just teasing him about the fact that I've known him since he was a graduate student at the Hawaii Institute of Marine Biology. And he has been one of the researchers who has done a phenomenal number of studies working across the archipelago with sharks and other fish. So without further ado, Dr. Meyer.
Kathleen, thank you for those kind words of introduction, and thank you all for coming this evening. It's an honor to be here and have a chance to share my research with you. Some 2,000 years ago, the Greco-Roman poet Oppian wrote the classical equivalent of an encyclopedia of fishing and fishes. And even though his work, Haliotica, is 2,000 years old, it contains many ecological observations of fishes that are just as valid today as they were back in Roman times. For example, Haliotica contains many descriptions of the preferred habitats of fishes of the Mediterranean. In this case, Oppian explains the types of fishes that you would find in places where there was seaweed. Now, in addition to providing a lot of detail on fish ecology, Oppian also noted that the tracks of fishes were a complete mystery to him and his contemporaries. And as he put it, the tracks of the swimming tribes are unseen. And it took 2,000 years for technology to advance enough for us to start changing that and being able to see where fishes travel in the ocean. Now, the reason that the movements of fishes are so mysterious is simply because the ocean's a concealing environment. It's very difficult to observe what's going on underneath there. And in the 1960s and the 1970s, biologists first started to attach tracking devices to fishes. Initially, small radio tags, and then in the 1970s, small acoustic tags. And the principle behind this is really simple. You put one of these transmitters on a fish, you then climb into a boat that's equipped with a hydrophone that can detect the signal from the transmitter, and a receiver that can translate the signal into the audible range, and then you just drive around following the beeps. And wherever the beeps are, that's where the fish is, and that's how you build up a picture of where fish travel. Now, by the 1990s, these systems were compact enough to be able to fit them into a kayak, which is great for reef fish research. And in fact, some of my earliest active tracking experience was in a kayak following reef fishes like this yellow striped goatfish known in Hawaii as the veke. And by tracking goat fishes, and here's an example from Coconut Island. This is basically 2 days and 2 nights in the life of a veke. And what this particular fish did was nothing very much during daytime. It would hang out in a school with other veke and not really go anywhere. But as soon as the sun went down, it became very active and roamed extensively over the sandy, flat area on top of the reef at Coconut Island. And at sunrise, it went back to its little resting area. And it did this on successive nights. So our very early tracking work with reef fishes suggested to us that reef fish movements are both rhythmic in nature and also highly predictable. Now, the problem with active tracking is that you can only sit in a kayak for so long and follow a fish. So the research, although active tracking is still an important tool, fish trackers move to using passive acoustic monitoring. And this is basically the same technology that we use for active tracking, but instead of sitting in a boat, we put down underwater receivers at places of interest on the seabed, and then we implant transmitters into sharks and fishes. And whenever one of these transmitter-equipped animals comes within detection range of one of these receivers, its unique identification code is recorded. And that these receivers can stay on the seabed 24 hours a day, 365 days of the year. So you're able to answer much longer term questions about the movements of animals. And this is an example of some long-term movements of a parrotfish at Coconut Island. And this particular panel shows color-coded receiver positions around the reef at Coconut Island. And this panel over here is 10 months of detection data, and the colors of the points correspond to the colors of the receivers. And the thing to point out here is the consistency of the parrotfish's behavior. By day, so the 10 months are on the x-axis, the time of days on the y-axis. By day, all of these red points, you can see that the parrotfish like to hang out in this area. Dusk and dawn, it would move up and down the reef. At dusk, it would head up to one of 2 sleeping places, either by this pink receiver or this black receiver. And if it went up as far as the black receiver, it would pass the yellow one. Hence, you get this sort of line of yellow here. And what you can see is that this particular fish showed the same basic patterns of behavior using the same daytime area and just a couple of sleeping areas every day for the 10 months that we did this study. So you can see that these patterns persist over longer periods of time. And this, in fact, is the very parrotfish that these data come from. And there's actually a little cleaning station right here. And you can see this parrotfish being cleaned by some of these cleaner wrasses. So we also see a lot of rhythmicity in sharks. And this particular example is from a scalloped hammerhead shark that was tagged off Kaneohe Bay. And there's about a week of data here. And during daytime, which are the non-shaded columns, you can see that this hammerhead typically stayed in the surface waters between 0 and 100 meters. That's between the surface and about 300 feet of depth. And that's the sort of shallow mixed layer where we find the warmest waters. By night, the shark dove multiple times down to depths of 600 meters or more. That's getting close to 2,000 or over 2,000 feet in depth, where it experienced temperatures down as low as 5 Celsius. That's about 42 Fahrenheit. Now, just to give some context to that, right now, the surface sea temperature in Dutch Harbor in the Aleutian Islands is around about 42 Fahrenheit. So this is an animal that can withstand moving from tropical surface waters down into essentially Arctic conditions and back again multiple times in a night. Very interesting behavior. And when we see patterns like this, we want to interpret them. And it's tempting to imagine that the reason the shark does this is because it's going down to feed on some organisms in the deep water. The problem with telemetry is it only tells you these kinds of tracking tags. This is from a pop-up satellite tag, by the way. It tells you where these animals went, but it doesn't tell you anything about what they're actually doing. And we have to be careful about interpreting tracking data, even when there's sort of compelling circumstantial evidence. And I'm going to use shark feeding as an example of this. So here we are up in the monument at French Frigate Shoals, which is an important nesting area for a couple of species of albatross. And fledging of the albatross happens for several weeks each summer. Keep your eye on the bird, normally during June and July. Oops. So as you can see, tiger sharks capture and consume some of these fledgling albatross. So you can actually see that firsthand up at French Frigate Shoals. A very unusual set of circumstances because most of the time we simply can't see sharks feeding. They come in shallow, the birds are very naive, watching, he's like, oh, what's happening over there? No idea really about what's going to happen to him next, probably. Okay, boom. But that one, the final one, I ended on a high note for the birds. That one got away. So the footage that you just saw was all taken in this little lagoon area here and out here at a location, a sandy islet called East Island, which lays more or less in the center of French Frigate Shoals Atoll. And we have one of those underwater receivers right here. And over some time, we've been up and we've captured and tagged some of these tiger sharks at French Frigate Shoals to find out what they do. And here is an example of some data from one of those tiger sharks. There's 2.5 years of data here along the x-axis. Time of day, once again, on the y-axis. And nighttime is shaded here in a light gray color. And I'd like to draw your attention to the clusters of red points that you can see here, which correspond to detections of this particular shark on that East Island receiver where you saw the tiger sharks catching the albatross. Now it looks like this shark shows up at French Frigate Shoals, and these clusters, by the way, coincide perfectly with fledging season. It looks like the shark shows up at French Frigate Shoals, stays there for fledging season, and then leaves, and then comes back again for another fledging season, and then leaves again at the end, but it's gone in between. And because this shark had both an acoustic tag and a satellite transmitter, we're certain that it left. In fact, this particular animal, after leaving here, went all the way up to this oceanographic feature we refer to as the chlorophyll zone transition front, or something like that. But it's a highly productive area where a lot of apex predators can be found feeding. It's where a lot of longline fishermen will try and set for tunas and things. So it makes for a really interesting and compelling story. This shark is roaming around, but it knows when to come to French Frigate Shoals for fledging season so that it can have an easy meal of those naive albatross as they make their maiden flights. The problem is that all these telemetry data tell us is that this shark was at French Frigate Shoals at the right time of year. It doesn't tell us that it ate any birds. It doesn't tell us that it chased any birds or anything like that. So you have to be a little conservative about interpreting these kinds of data, even when the circumstantial evidence is very compelling. And what we really need are things that can actually measure ecological events like shark feeding. And if you think about the mechanics of shark feeding, you notice that sharks are not big chewers. They tend to bite off big chunks, or they eat their prey whole, and then they swallow it down. And most of the processing is actually done in the stomach. Initially, when the prey is swallowed, the shark swallows a bunch of seawater and chunks of whale in this case, and these sit in the stomach, and then they're steeped in a mixture of acid and enzymes for a period of hours to soften them up before the stomach actually starts physically contracting. And then it mashes the prey up more and more and more until it reaches the consistency of a smoothie, at which point it's squirted further down the digestive tract. And we hypothesize that those profound changes that occur in the stomach contents should be measurable somehow. And what we decided to try was using very, very weak electric currents. When the meal is digested, it releases fats into the stomach contents. And as more and more fats and oils get released, it's harder and harder for current to flow through that medium. So if you have a device with two little electrodes and you try and pass a current through it, the current's passage gets harder and harder over time. So we were working with these prototype tags, and what we do is we disguise them in food, and then we feed them to our captive sharks that we have out of Coconut Island. And we take advantage of the fact that sharks naturally regurgitate indigestible materials. So they basically cough up the device after a period of days or months, and then we're able to download it and see whether we can see any feeding signal. And here's an example of some feeding data from one of our captive tiger sharks. And there's about a week of data here. And during that time, we fed the animal twice. On the top here, you can see a temperature line. And we actually use cold food so that we have a thermal reference point in the record against which to compare our impedance values. The first meal was around about 8 pounds in weight. The second meal was around about 5 pounds in weight. And as you can see, there's a very clear signal that follows feeding, both for this meal and also for this meal. And so we do have the essential signal that we can use to directly measure feeding in sharks. Excuse me. So you'll also notice that the peak of the 8-pound meal is wider than the peak of the 5-pound meal. So there's some information in there on meal size. And we're still developing this technology. Right now it's still in prototype form, but we're hoping to be able to take it out into the field and feed it to wild sharks, who will then regurgitate the tags, which will hopefully be able to recover using telemetry to get the first ever records of wild sharks feeding. There are some other devices that we have been using for several years that also help to give us more insight into how sharks are using their natural habitats. This particular device is a triaxial accelerometer magnetometer data logger, which is a bit of a mouthful. So I typically just refer to it as a flight data recorder for sharks. This, by the way, is a prickly shark. Excuse me. Enjoy the video while I try and recover my voice. So these devices record, excuse me, I've got a cold, which is why my voice is cutting out. They record multiple channels of information, and things like depth, temperature, swim speed, 3 axes of acceleration and 3 axes of magnetometer. They're data logging devices, so we have to go out and physically recover them. And we do that. They have a release mechanism that releases them from the shark. And then they float to the surface, and we use the telemetry transmitters to go out and find them. And here's an example of what the data look like. And we don't have to get into the details too much right now, but there's depth, temperature, swim speed, 3 axes of acceleration, and 3 axes of magnetometer, which are from the compass. Thanks, Kathleen. If we take a close look, before I get into this, you'll see that for the most part, the shark's sort of up in the mixed layer with that's between 0 and 100 meters, occasional deeper dives. Its swim speed is typically about 0.5 meters per second, and that's only about 1 mile per hour, and that's typical for these animals. They kind of plod around through the ocean. There's some occasional burst speeds of up to 3 meters per second, which is about 7 miles per hour. And to give you a frame of reference, the record for a human Olympic 50-meter sprint swimmer comes out at about 5 miles per hour. So you're going to have to swim very fast and have a head start if you want to escape from one of these animals. This is a closer look at one of those dives. And as you can see, the shark went down to 400 meters. And then there was this little burst in swim speed when it was at the bottom. And you can see that that's reflected in the accelerometer. You get a little knot of activity there. And that's caused by the shark's tail beat activity. And when we run what's called a spectral analysis, we can tell that the shark was beating its tail about once per second. And that for this burst swimming event, the amplitude went up to generate the speed. I'll take some questions at the end, okay, so just hold that thought. Now, we have a lot of vector data from these packages, so we can actually do three-dimensional dead reckoning reconstruction of the animal's tracks. And here, we're looking down on a segment of tiger shark track, and it's in a box that's about 600 by 400 meters in dimension. And what I want to draw your attention to are all these little curlicue spirals. As the shark swims along, it's suddenly circling around, and it does it again, it does it again, it does it again. And we refer to this as hypergyration. And before we had these flight data recorder-like devices, we had no idea that this kind of thing went on because we just didn't have something with sufficient resolution to capture this kind of behavior. So you can see that these very sophisticated devices gives a lot of information on the sort of mechanical aspects of swimming, but they still don't really tell us anything about the context or the purpose of this behavior. So, you know, why is this animal doing all of these hypergyration spirals? So to help us get some insight into that, some of these packages also have really small video cameras attached to them so that we can get a shark's eye view of what's actually going on. Now, there's no guarantees that we'd even get one of these things back. Imagine you put this package on a tiger shark, you let it go, it swims out into the ocean, does whatever it does. You know, it's a big gamble. So we're really delighted, A, that we got them back, and B, that we actually did record some pretty cool data. So here is a big male tiger shark caught off Kaneohe Bay, and he's wearing one of these camera packages on his pectoral fin. And in a minute, we're going to see a little bit of footage from the camera. That's a big guy. He's about 14.5 feet long. Okay, so you can see that to start with, he's swimming, just kind of swimming over the reef. But in a minute, he sees something, and he does a burst swimming event. You'll see the reef kind of go crazy at the bottom of the frame, back and forth, back and forth, back and forth. And then he gets to the end of that burst swimming event, and you'll see him start to go into these tight turns. So he's obviously seen something interesting. You know, when I first downloaded the camera and I saw this happen, I knew he'd seen something. I had no idea what it was. I was like, eat a turtle, go on, eat that turtle. But there was no turtle at the end of the rainbow. And what he sees, you'll see in a minute, is another tiger shark. And there's a little slow motion loop in a minute because this is kind of brief. But what I can tell you is that there are no claspers here, so we know that this is a female tiger shark. And as he goes up to her back, you can see some mating scars on the dorsal ridge. So this is a female that's been involved in some mating activity before. She wants to have nothing to do with it. And you can see the eye roll in a minute. There we go. So we actually targeted this deployment during peak mating season, which is in wintertime in Hawaii, hoping that we would get something like this, but never thinking that we would. So we were pretty pleased. My only disappointment was that he didn't seal the deal. You know, this female ran away, and that's all that we got. But it was a pretty cool result. And we've been putting these cameras on a variety of different elasmobranchs in Hawaii. This is an example from a Galapagos shark. Again, this is the camera shark here, and he's wearing the camera on his pectoral fin. You can see the side of the head and the eyeball in the frame. And he's just sort of like gliding through the ocean in close formation with another Galapagos shark. And you can catch glimpses of the reef as they sort of wheel and turn. And there's a bunch of reef fishes. And we think this is off Kahuku Point, this particular footage, based on where the camera package came up. And those are smooth unicorn fishes that you can see that the sharks are swimming through, that they're sort of, the fish are getting out of the way, but not in any real hurry. And this is also another example with Galapagos sharks. And keep your eye on the little fishes behind this animal. These are apelu, which are basically candy for any kind of predator. But instead of running away from the shark, they actually swim up to it and use its rough skin as a convenient scratching post. And that's pretty remarkable footage, considering that it was filmed by another shark. Now, we've also got some really cool insights into less glamorous elasmobranchs that live in really murky water, like this Hawaiian stingray. Once again, this is in Kaneohe Bay, actually, and we're about to release this animal with the accelerometer camera package on it. Now, when we were thinking about this study, we thought, wow, we're going to get a lot of camera footage of mud. These animals are going to sit for hours in the mud, and maybe if we're lucky, we'll get one or two things. We were completely wrong. It turns out that stingrays are incredibly dynamic. They hardly sit in the mud at all. And in fact, here's a little bit of spectacular camera footage from the stingray. You can see his wing going up and down. He's on the seabed there. And he's about to take off and sort of head up towards the surface. And you watch his wings. He's going to work harder and harder and harder as he takes off, and you can see the light get a little bit bluer. This is Kaneohe Bay, so he's on the bottom in like 40 feet of murk. But watch what happens when he gets to the top of his dive. Now he's turning back down. You see how the wing stops? And he just glides back down to the seabed, which you'll see in a minute. There it is. And when we actually looked at the accelerometer data, we found out that A, they just do this all day long, and B, that they actually conform to something that that's known as a classical fly-glide energy-saving strategy. So here we have the depth of the stingray, and he's going from about 40 feet of depth up to close to the surface, back down, up, back down. You'll notice when he goes uphill, it's steeper than when he goes downhill. Uphill, downhill. When you look at the acceleration, which is basically the amount of wing flapping he's doing, he works really hard to go uphill, and then he just stops. So he's gliding all the time going down. Now, the reason animals do this, and you can look outside and see songbirds and things do it, is that it actually takes less energy when you are negatively buoyant to move through the ocean by working hard for a short period and then gliding for a long period than if you just swam continually. So it's actually an evolutionary adaptation. But it actually takes more energy than just sitting in the mud, which is what we thought the stingrays would do. We still don't know why it is that they exhibit this type of behavior. We're working on it. I think the single most impressive piece of footage that we got from the cameras, a sandbar shark, a relatively small species that's common in our waters. And this particular individual started the day down at about 300 feet, suddenly ran into a bunch of uluas, and then we started to see sharks show up. In fact, they were hammerhead sharks primarily, but then we saw there were other sharks. There were other sandbars and some oceanic blacktips, Carcharinus limbatus. And during the course of the day, more and more sharks joined this aggregation, and it got larger and larger. There's another sandbar shark. And it gradually rose from the seabed up into the water column. And we could see there's an oceanic blacktip, Carcharinus limbatus. As some of these hammerheads came past the camera, past the sandbar shark, look at that one, you can see it's got claspers. So we know that this is a reproductively mature male, which gives us a sense of size. And then another hammerhead of a similar size comes past, and this one has no claspers, so we know it's a female. So we're able to get some information about the demography of the aggregation out of the camera footage as well. Now, this is happening mere miles from where I'm based at Coconut Island. But until we started doing these camera studies, we had no idea whatsoever that these mixed aggregations of sharks formed in our waters. So it was a pretty exciting discovery. Now, we've also been using this technology to study some of Hawaii's deep sea sharks. And what you can see here is a blunt-nosed six-gill. It's actually a pretty common shark in our waters, but one that you're very unlikely to meet because they never really come shallower than about 1,000 feet. And you can also see that they're pretty big. So a couple of years ago, we did the first ever, anywhere in the world, camera deployment on one of these blunt-nosed six-gill sharks. Again, this is a big animal. This animal is about 13 feet long. And, you know, we got the camera back and got some interesting, cool glimpses of the animal's deep sea habitats and the sort of strange creatures that it encounters. And by the way, this is a still camera instead of a video, because we wanted to use light so we could see the pictures, but we didn't want to disturb the behavior too much by having the light on all the time, so we went for the still camera instead of the video. And we found out that those images were actually captured in the deepest part of the six-gill's daily movements. This is, I think, a week or so of data. They're diel vertical migrators, so they go deep during the day and less deep at night. So they range between about 2,000 feet, well, about, depending on the individual, about 3,000 feet at their maximum depth, up to about 1,000 feet at their shallowest. So these are animals that are living down at about 2,000 feet below the surface. But the coolest thing for us was actually not the pictures. It was a completely unexpected discovery about their swimming. You can see here is a dive of a blunt-nosed six-gill. Here it's going downhill, here it levels out, and here it goes uphill. Now, when we look at the accelerometer data, and I'll draw your attention to this, this line here, this big fuzzy part here tells us that it's working really hard to swim downhill. When it levels out, the pace actually lessens, the tail beat lessens. When it starts to go back uphill, it actually stops altogether. So the reason for this, and it's something that nobody had seen before and nobody expected, is that these deep sea sharks are actually slightly positively buoyant. They can glide uphill, but they have to work to go downhill. And again, we don't know why these sharks are positively buoyant. And we're hoping to figure that out soon, because we've just, in collaboration with colleagues at University in Florida, have developed some night vision video cameras that we're hoping to deploy very soon on these deep sea animals to try and give us a sense of what it is, how they're using this positive buoyancy in their deep sea habitats. Okay, I think I'm a little ahead of schedule here, but so the main point that I want to get across to you tonight is, first of all, that technology like these satellite tags that I'm putting on a tiger shark has really helped us to gain exciting new insights into the ecology of sharks and fishes in our oceans. But we still have a lot of questions still to figure out. You know, there's a lot of mysteries about the ecology of tiger sharks in our coastal waters that we still need to work on. And if you guys are interested in following our research really closely, you can go to the PACIRS website and you can see some of our satellite tracks in near real time. And this particular example actually is from a shark that we tagged off Kihei, Maui. We wrapped up recently a big study around Maui. But if you go on that site today or later on, you can see some tracks, some recently posted tracks of tiger sharks that we tagged around Oahu over the last couple of months. And one may be coming to a beach near you very soon. Okay. And finally, it's really important for me to acknowledge that the stuff that I've shown you this evening is the product of a team effort. There's a lot of people that help out with this research and a lot of funding support from different agencies. So I'd just like to take this opportunity to thank all of those, those people and those funding groups for the support that makes this exciting research possible. And thank you very much for your attention. And I think I've got my voice back enough to take any questions that you may have. I'll take Les and then Mr.
Because the footage of the sharks sitting fledgling albatross have anyone answer what in the chemistry of the bird makes it a useful food because sharks eating anything?
I think the key to that, to be perfectly honest, is the ease of capture. And so, to me, a tiger shark eating albatross fledglings is like me eating popcorn. You know, it fills me up, but I'm hungry again really quickly, but it's easy to eat. And the same is true of these birds. You know, there's really not much protein or energy value in each individual bird, but they're so naive that what happens every day is that the tiger sharks come to that fledging site and they just eat and eat and eat until they can't eat anymore. And you can watch it. And I've spent a lot of time, I've been fortunate enough to spend a lot of time in that area watching it happen. And you can see that first thing in the morning at first light, the sharks are rapacious. They're taking down those birds explosively. The birds don't stand a chance. If you're an albatross, the key is to do your maiden flight at about 12:15 in the afternoon. Because by then, the sharks have eaten so many birds, they couldn't care less. You know, you just land in the water and they're sort of like swim past you and leave. So I think the crux of it is that it's just very, very easy calories for those sharks. But for me, the intriguing thing is, how do they know? And if you think about it, sharks are not like bears. You know, the females don't teach the pups where to find food. The female shark just drops her pups and they're on their own. They have to figure it out. So the only way that those phenomena can happen is that sharks stumble upon them by chance. And our tracking information suggests to us that although sharks have home ranges like everything else, there's always a component of exploration in their movements. So what probably happens is that every now and again a shark sort of goes somewhere different where it hasn't been before. If it finds something to eat, then it sort of adds that to its mental map and knows that that's a place where it can find certain types of food. To pull off this thing, where you show up at the beginning of fledging season, just in time to eat those birds, first of all, you need to have found it in the first place somehow. So you have to be there at the right time of the year just to stumble upon it. And bearing in mind, it's only 3 weeks a year, more or less. And then you have to have some kind of internal clock that allows you to know when June 15th is and it's time to go to French frigate shoals and eat birds.
After you put the accelerometer on the shark, has anybody observed a shark trying to get rid of that device?
We have not seen that. Excuse me. But certain other types of devices that we put on externally get knocked off by the sharks. They either get knocked off by the sharks or because they look a bit like fish, it may be that they're a predator strike, so something like an ahi comes by and busts it off. But with our accelerometers, because we have such high resolution data, we would literally be able to see if the animal was turning and trying to bash the package. It would show up in the data, and we haven't seen that. And it's always a concern to us when we instrument these animals that the stuff that we're putting on may be impacting their behavior, but we're sort of greatly encouraged by the fact that even though we put this bright yet orange thing on sharks, they still want to hang out with other sharks and actually mate with other sharks if they have an opportunity. So we feel that the behavioral impact is relatively small. And when you see them swimming in a school of other sharks and the other sharks don't seem to care about it either, you know, it gives us a lot of confidence that it's not as much of an impact as you would think. And those packages are built to be neutrally buoyant while they're on the animal. So the only real, there's a slight drag impact and the fact that you've got something bright and orange on your wing. Those are the two things.
What's the status of the Galapagos sharks that have been trained on Galapagos?
So the Galapagos sharks are doing just fine. And, you know, so this is something that I've actually done quite a bit of work on. in the monument. And the punchline is that it looks like there are a subset of individuals, Galapagos sharks, that utilize these the reef areas around the pupping sites in the atoll. But so there's probably a subset of Galapagos sharks that are responsible for most of the shark predation on monk seal pups in any given year. However, the same study showed that there are other individual Galapagos sharks that just kind of blow through that area periodically. And we think that that's probably the on-ramp for pup predation behavior, in the same way that if tiger sharks are going to eat albatross, they have to find the albatross there in the first place. So in addition to these Galapagos sharks that have these pupping areas as part of their core home range, there are other individuals that are just kind of blowing through but using the rest of the atoll most of the time. If they happen to come through when there's some blood in the water or they encounter a vulnerable pup, that's how they probably learn that the prey are there. So it's a natural phenomenon that's of concern to the management of the critically endangered monk seal. But my personal opinion is that the culling of those Galapagos sharks will perhaps buy a short-term reprieve, but because it's a natural phenomenon, there's going to be many more waiting in the wings, and that the same thing is going to re-establish over time. That said, I've had some back and forth with the monk seal folks on this. I'm at the point where I'm like, well, you're claiming that culling out these sharks is going to solve the predation problem. I don't believe that's going to be the case. But if you cut, the only way we can really answer that question at this point is to cull sharks, which is actually a lot harder to do than people might imagine. I mean, I catch sharks for a living, and we went up there and for the tagging study with the Galapagos sharks, we caught 70 odd Galapagos sharks in 3 months. The monk seal guys catch 1 or 2. Is that right, athlete? Something like that. Only ever 1 or 2. So it's kind of a hypothetical thing, and I completely understand their dilemma. But they're trying to recover the species. Every single pup is valuable. I totally get it. I also agree with them now that it's probably Galapagos sharks that are primarily responsible for this predation. However, it's a natural system that these things have co-evolved for millions of years. And so I just feel that it's like, tinkering with a natural system, and it's turned out that it's much harder to implement than it looks on paper. So I hope that answers your question. Okay, Les?
The parrotfish you showed before.
Yes.
You showed it had 2 sleeping sites, one part of the year. You do that over a period of years to see if that was seasonal, or just change from one site to the other side.
So we didn't have quite, so those transmitters we put in the parrotfishes lasted not quite 2 years. So we didn't really have enough. We had some evidence of seasonal changing of sleeping areas, and not just in the parrotfish, but some of the other reef fish that we tagged. But we didn't have quite enough cycles to definitively prove that. And that's one of the challenges with this type of technology, and it's something that I'm pushing towards now, is putting out transmitters that last for a long time. So recently I've been putting out transmitters in sharks that will last for 10 years. And in fact, we did some preliminary stuff in 2007, and we now have some sharks that we have tracking data for up to 9 years. So, okay.
Can you hypothesize a little more on the big school of sharks and what was going on there?
Yeah, that's a great question. So why do sharks hang out in these big mixed species schools? And the answer might surprise you. And I think the most likely reason is that it's actually an anti-predation function. If it was a mating function, then you wouldn't have more than one species in there, right? So it's like black tips can't mate with hammerheads, so there's no reason for them to hang out together. The evidence that we have suggests that these sharks probably feed a lot at night, and this was a daytime phenomenon, so it doesn't have anything to do with feeding. Although it seems hard to imagine, sandbar sharks, blacktip sharks, and hammerhead sharks are actually prey for larger sharks like tiger sharks and white sharks. And so throughout nature, schooling and herd formation is quite commonly an anti-predator defense. And we suspect that that's one of the likely candidate explanations for why they're forming these aggregations. It might not be the only one, but we think that's a probable explanation. Yes, sir.
Yeah, any comments on the overall population of the different shark species, any trends that you've observed?
Well, that's a great question. And are you talking in Hawaii or globally, or?
Archipelago.
Okay, so Hawaii is one of the best places on earth to be a shark, really. And the reason is that there is just no shark fishing here. Obviously, we've got this fantastic monument that's enormous, and nobody fishes in there. But guess what? In the main Hawaiian Islands, people are not interested in catching sharks like they are in other parts of the world. But that's because of cultural reasons. You know, sharks are very important to Hawaiians and other Polynesians, and because there are way better things to eat in our waters than sharks, and also because of legislative acts banning shark finning. You know, there was a sort of fledgling shark fishery back in the 1990s that was because of the lucrative nature of the shark fin industry. And in fact, even when I was out snorkeling, I remember I was snorkeling Waimea Bay one day and I found a dead finned tiger shark lying on the bottom that somebody had caught with their ulua gear, reeled it in, seen, you know, sort of Saturday's beer money, and just chopped those fins off and threw the rest of the animal back. But since, you know, laws were passed and stuff, that sort of went away. So there's really no significant fishing pressure for sharks here. There's plenty of stuff for them to eat. Most of all of these sharks are predators of reef organisms. Most of the reef organisms that they consume are not targeted by people. So there's plenty of stickfish and pufferfish and, you know, things like wrasses and things like that. So Hawaii is a great place to be a shark. So I would say, despite what you might read elsewhere, that the shark populations in Hawaii are in near pristine or pristine condition, the coastal shark populations, which is certainly not the case in many other parts of the world. And by the way, it's very difficult to assess population size of sharks because the types of techniques that biologists typically use, mark recapture, require an understanding of immigration and immigration rates and things that are either, you know, basically very difficult to nail down for sharks. So we could come up with a number, but it would have massive error bars around it. Yes, sir.
One of the pictures you showed shark migration looks like east and west. Do they also go down south below the equator and above? What kind of a history or pattern do they have for their swimming?
So you're talking about shark migrations around the oceans in Hawaii?
Northern as well as southern hemisphere.
So what our tracking has shown us is that most of the types of sharks that we have in Hawaii, coastally, are predominantly residents around a single island, right? They don't, you know, they move around the island and maybe they'll go to a neighbor island, but they're not going very far, for the most part. There's some exceptions. One of the Galapagos sharks that we tagged at French Frigate Shoals during the monk seal park predation study was subsequently detected at Palmyra Atoll, which is about 2,000 kilometers. The exception are tiger sharks. So they're the one species that we have here coastally that are common, that are much wider ranging, at least some individuals. The most common migration you'll see is just up and down the Hawaiian chain. But you also see them go up into high latitudes or higher latitudes and down into somewhat lower latitudes. But But it's rather than going to a place, going from one place to another, it's more a case of sort of, they're like satellites of the archipelago. So it's not like they leave and they all go to Tahiti or something. They sort of go out, and sometimes we don't know why. We had one we tagged on Maui that showed fairly typical tiger shark behavior, staying in coastal waters a lot. And it took off, went basically 1,000 miles south in a straight line, and then just turned around and came straight back. It didn't seem to go anywhere at all, and we don't know why it did that. And others do these sort of curlicue loops and stay at sea in open ocean for months at a time. And we think that those are out there eating seabirds and things like that. Now, we've had a couple of exceptions. So we had, ironically, the devices that I like to use, kind of expensive. Acoustic tags are $350 a piece. Those flight data recorders, they get up to like $10,000, $15,000 for a package, $20,000 sometimes. We used a $1.25 ID tag. This is what we call a spaghetti tag, just like a license plate sort of thing that we put on all our sharks so we can see that it's tagged. And we had one of those animals swim to the Sea of Cortez, which was a bad choice because it was captured by Mexican fishermen and processed into various things on the beach. But there happened to be somebody with several degrees of separation from us who saw the shark, saw the tag, saw the thing, and got it back to us. So I actually have that tag that came all the way, went all the way to Mexico, came back via the US Postal Service. So we do see some migrations. They are not the same as you see with some, even with, say, tiger sharks in the Atlantic, where they sort of will be in the Bahamas and they go north during the summer, out to the mid-Atlantic, and then come back south during the winter. The tiger sharks and other sharks here don't do that. Most of the sharks are pretty resident. So an Oahu shark will just swim around Oahu, visiting its favorite places. And the tiger sharks, they move further, including from Kure Atoll all the way down to Hawaii Island. We've seen individuals do that. But it's typically very much orientated to the archipelago itself.
That fishing for sharks for food, because young fish are here for food, what parts of the world, some places I guess they're so thin, but with the decrease in other food in the ocean, the more sharks ending up on the table.
Absolutely, and I mean that has been the case for a long time. So as you can hear from my voice, I'm not from around here. I grew up in Britain. And over there, we used to have this thing in the fish and chip shop called rock salmon. Guess what that was? Shark. In fact, it was spiny dogfish, which was as common as muck 30 or 40 years ago, and now is the spiny dogfish stocks are in dire straits in Europe. So Hawaii is kind of the exception. I mean, you look around the world, and there's a lot of places where shark populations are in trouble, and fishing is the reason, and in two forms. So there's the targeted fishing, where people are going after them for the fins, for the meat, and stuff like that. So they're actually going out to kill a bunch of sharks. But what most people don't realize is that a lot of sharks die as bycatch in other fisheries. And one of the biggest culprits is the tuna purse seine fishery. And as long as we want to go to the store and buy a can of tuna for $2, or maybe $1.50 at Best Buy or something like that, there's going to be industrial scale fishing, and when because they saved the dolphins, they don't set on dolphins anymore. They set on a lot of drifting fads, and under those fads are a bunch of sharks. And if it gets wrapped in the net, it's basically dead. So there's a lot of problems, and a lot of fisheries have, once they've taken out the prime fish, sharks are sort of the next thing that they can take, and then they remarket those. So we're seeing that happening around the world, and the shark fin industry is still growing because the middle class is growing in China, which is where most of the demand is. And so that is a problem, particularly for nations where fisheries are poorly regulated. People come in with suitcases of cash and buy fishing rights, or don't even bother, and shark populations are being decimated as a result.